Hello, and welcome to another video in this series as we learn the basics of Prolog together. Today's video is the last one on the topic of metaprogramming. So over the last few videos we introduced the idea of metaprogramming, that is, writing Prolog to run Prolog programs, and we said that the reason for doing that was to either change or extend the way in which Prolog is executed. And you don't normally do that. You don't normally write Prolog to run Prolog unless the problem you're trying to solve does require a change in approach that the vanilla Prolog doesn't easily let you achieve. We, over the last few videos, have started with a very minimal Meta-Interpeter, and over the 2, 3 or 4 videos we extended it a little bit at a time because we didn't want to rush it, and we wanted to kind of let the core ideas sink in and see if there's a kind of a pattern to meta-interpreters, and we saw that there was one. Up to now our meta-interpreters have extended beyond vanilla Prolog by printing out explanations for the proof of a query. What we're going to do today is look at a different use, a different benefit of metaprogramming, which is to actually change the execution strategy, the way solutions are searched for in Prolog. And one quite fun example to apply that to is kind of solving mazes or searching for paths through mazes. It kind of brings it to life. But the application of that idea of changing the execution strategy is applicable much more broadly. So let's dive in and talk a little bit about the problem domain that we've created for ourselves. So on the screen we've got a map, a maze, a plan of a castle perhaps, and you can sort of see these things that are rooms. We've labelled them A, B, C, D, E, F, G, H, I, and we've got links between them, and we can encode this universe in Prolog. We can list facts to say link goes from A to B, so that is true. If we said link A, E, there's no direct link from A to E, so that's not listed, in our, that wouldn't be listed in our database. So we're just linking, we're just expressing facts about adjacent rooms, like that. And if you look at the example code, at the top you can see a bunch of facts called link, which just express those links: A to B, B to C, A to D. So A to B, B to C, and the other one was A to D. That's the top 3. Yep. D, E, E, F, G, H, D, E, E, F, and G, H. Did I say G, H? D, G, sorry. Yep, D to G, because G to H does not exist, and H to I does not exist, and E to H does not exist. The other one is FI. FI, what's this one? FC. F to C, yep, that's in that direction. Notice it says F to C, not C to F. Let's have a look. F to C, not C to F. So that should get us thinking a little bit about direction. If we say there's a link in the database F to C, do we want C to F? Do we want link F to C to be true, or something that represents kind of a journey in the other direction? Because ultimately we're going to be kind of working out journeys. Let's see, maybe from here to like that sort of thing. and that would mean going from A to B, B to C, C to F, F to I. So C to F is not F to C. So we need to express another concept of connectedness, whereas this link is more about a unidirectional connection. Now we could have we could kind of write down link F to C in the database, and do that for every connection, so we have a link factor for both directions. We could do that, but in our example, let's imagine we don't have that. We're given these from another source, for example, I don't know, a mapping company or a database of kind of describing a location, so we don't have that with us. So we can do that quite easily. We can say connected x comma y. That's true if link x comma y, or connected x comma y if link y comma x. So it's the other way around. Let me just colour that. X and y. So connected F to C, because link, so let's write that down, connected F, which one's in the database? So F to C is in the database. Let's imagine we're asking CF, because this is in the database, but this isn't. So connected C to F is true if link, the second one, y to x, so F to C. So that's true, and therefore this is true. So it just catches both cases. That's not too difficult. We should be quite familiar with being able to do that. Let's test that just to get our fingers warmed up. So let's just test link A to B, just to make sure that's true. Yep, as expected. And F to C is true, but C to F should not be true. They're false. And let's look at a link that just doesn't exist, E to H and H to E, that doesn't exist. So link E to H, E to H, false, and H to E, and that should be false because the link doesn't exist. Great, now let's test our connected. F to C is in the database, so C to F, is that connected? True. And the very basic case of something that does exist in the database, F to C, that should be true. Oh, it's asking to see if there's another answer, and it's false. So this is true, and that's because it's backtracking. It's found this to be true, and then it's moved on to that one. Now we could stop that with a cut, but we're not going to today, because today's purpose is not to think about the cut, and it's not really to think about meta-interpreting the cut. So what we'll do is we'll put up with the odd occasion of a correct answer and then backtracking to false. It's not going to really pollute our results, as we'll see later, so we won't deal with that because we want to keep our code as simple as possible. So that's the reason we'll tolerate that for now. Great. So let's think a little bit about a full journey between two arbitrary points. So let's start with a simple example of a journey between A and C. So it consists of two steps, from A to B and then from B to C, and we can write that down as A to B and then B to C as 2 steps like that. So that's the journey. We could write it as a list even, like that. In fact, this is interesting because what we've done here is we've chosen a way of encoding a journey in terms of data, which is structured in this way. It's a list of steps, and each of the steps is a grouping caused by the brackets between 2 locations, X and Y. So you can have A and B, D and E, and so on. Of course, these 2 have to be next to each other, and that will be enforced by the fact that 2 points are connected. So just looking ahead a little bit there. So that's that journey. Let's look at another one. A to E. A to E would be A to B and then B to E. So that journey is a list of steps from A to B, same as that one, and then from B to E. In fact, it could be done another way. It could be A to D and then D to E. So let's write that down. A to D and then D to E. That's another possible journey to get from A to D. So you can start to see how this idea of a journey can emerge, where you could say journey is true between X and Y if, well, actually, in the input parameters, we need to say something is true or false. We need to have the list, the journey itself. So let's undo that a little bit. So X, Y, and then journey is true. So from here to here is true if this list J actually describes steps from X taking some route to Y. And how would we define that? Well, let's look at the simplest case. The simplest case would be if X and Y were just connected. So you could say connected X and Y, and the journey would be something like X, Y. Let's talk about what that means. So we're saying that this is true, this is true if X and Y are connected directly, like D to E, and J, and this is the bit that's not so obvious on, when you first think about it, and J is a list of steps, which in this case is just one step, a journey of one step, which is just XY. So let's write that down, instantiated as it were from D to E. So journey D to E, whoops, and then J is a DE, that's the steps. Is that true? That's true if connected DE and then J equals DE as just a single step. Now, have I done that right? Nope, that should be a J. Great. So that's just kind of bringing it to life with one very short journey. Let's think about what it might look like for a journey that's longer, because that was the trivial example. Right, let's think about a journey that's from A to F, A to B to C to F. So that's one possible solution. That step, and then that step. So we'll say that journey A, F is true if. So you can kind of start to think this is going to need a recursive definition, because we've got all kinds of journeys, short ones and long ones. We've already decided that, we've already kind of shown that the simplest case is journey x comma y if it's directly connected. That's a j. Directly connected x, y, and j equals x comma y as the step. Square brackets. So that's the trivial case, or the base case. Now we're going to do the recursive definition for longer ones. Remember how recursive definitions have a property defined in terms of itself, but the second reference to the same property is smaller by one step, or closer to the solution by one step. So we can think of this bit, journey, as having solved it by one step, which gives you a clue as to what the additional condition would be. So if this was A to F, this might be A to C, and then this might say that C to F is connected. Can you see that? Let's do that there. So this is sort of saying the journey from A to F is true if C to F is connected and A to C is a journey. Do you see? And then if you solve that, you could say that, different colour, you could say that A to C is true if B to C is connected and A to B is a journey. Then A to B is a journey in the trivial case, which is directly connected. If you need a little bit of practice on or a reminder on recursive definitions, we did a whole section on them, as in 2, 3 or 4 videos on that, so do go back and have a look or read the blog sections on those. So the journey from A to F with J as the list, it's true if C to F is directly connected, C to F. So we're not talking about variables here, we're talking about actual specific journey, and we're doing that just to illustrate the method. C to F is connected and there's a journey from A to C, and there's another journey, the list of steps, but actually there's a relationship between this and this, which is this one is this one with the last step removed. J equals C to F joined with J1. That's it. So J, the full journey A to F, is J1 with an extended at the top of the head by C to F. So the general rule is journey X, Y, J if connected. Let's think about which one that's going to be. The last step is Y. The first one we don't know. Let's call that Z. So it's, if this will be Y, this is X, so start at the end, and this one we don't know, so we'll call that Z for now. And then there's a journey from X to Z, J1, and J equals J1 with which one added to it? C to F. So that's Z to Y. That to that. Phew! So we got there in the end. So we have a recursive definition of a journey with the simplest case of directly connected positions, and then the recursive self-referential rule, which is arbitrary between distant points, and then by solving this you eventually reduce the problem by one step at a time until you reach the trivial case. Let's look at the code definition of that, which should be what we've just developed in code. So here's the definition in the example that's online on GitHub, and we've said the simplest case is journey xy, this one here. It's saying xy, and there's a j, the list of steps, which is just xy, if connected xy, directly connected. So that was the base case that we talked about. And then the more general recursive definition, so the one that self-referential, the continuation rule as it were, is to say that x, y and j are a journey if connected x to a. So I've chosen, this is doing it the other way around. This is working from the front forwards rather than the back. So we're starting at the front and saying x to a. So that's what does that mean? So we're saying here's a journey a, b, c, f. We're defining this one as the journey is true between a to d if this is connected and then this is a journey. What we've just talked about is the other way around. We've said that's connected and that's the journey. So it should be equivalent. If I didn't look at the code, I arrived at this version, but it's kind of solving the problem in a very equivalent way. So it's saying that journey is true if x is connected to some a, and there is a journey from that a to the final destination y, and that list of steps in the from a to y is if when appended or prepended with a step x to a is j, this full journey. So because this video isn't about recursion, I don't want to explain that too much. If you want to practice your recursion, do go back to the earlier videos on that and the blog posts. So let's just test this. So journey xy, let's do the simplest case, a to b. That should be true. Let's hope it is. Journey. Oh, it's of course that's wrong because we haven't given it a list of steps a, comma b. So we have to think a little bit about what this statement means. It's saying this is true. This is a true journey from a to b if the list of steps is ab. A journey of just one step. Now that should be true. Yep, that's true. And there's some backtracking going on here because of this. That's good. If I said a to c and the steps were ab, that should clearly be false. Yep. And if I said a to h is the step, which clearly isn't, there's no direct link from a to h, that should be false as well. Yep, that's false. Let's do a more interesting journey. Let's do a to c. So instead of, this is a journey of two steps. So a to c is true if there are two steps. So a to b and then from b to c. This should be true. Yep. We ignore the backtracking. Great. And in fact, let's see if a to c is true via a longer route. So AD, DE, EF and FC. So if I can remember that, A to D, that's the long way around, A to D, D to E, E to F, E to F, and then F to C. F to C. That should also be true. So A to C, this is a direct path, and this is a less direct path. And that's true, yep. Cool. Now, as you know with Prolog, part of the power is being able to not just verify true statements, but also to see how they could be true if we use variables. So if I say the last step, so last step, let's see what that last step should be to make this journey valid. So we're now using the power of Prolog to go through the database of facts and the connected relationship to see if it can satisfy a journey from A to C, which starts off with these steps, but we just don't know what the last step is. Let's run that. Last step is F to C. Fantastic. So you can start to see how Prolog might be helpful for journey planning or route finding or solving mazes. Let's see if we had last step 1 and last step 2. See if that is doable. So E to F and then F to C. Yep, it solved that. Fantastic. So this is looking really interesting. Let's see if we have a short journey where we are now going to just test it with no knowledge about the journey. So let's say A to B, and we just don't know what the journey is. It's a J, capital letter, so it's a variable. What would that journey be? A to B? Yep. Oh, it's found another one. This is interesting. Let's have a look pictorially what that means. So we're asking for journeys from A to B, and because we've left J open as a variable, we want Prolog to find what the journey is, what are the list of steps. And the first one it found was A to B, which was the trivial one, A to B, that one. But it actually gave us another one, A to B, B to C, C to B. What is that? Let's look at that one. A to B, B to C, and C to B. So that does get us from A to B, but it's a longer journey, it's less efficient, but it satisfies our definition of what a journey is, which starts at a place, ends at where we want it, and the list of steps is of directly connected steps. So that's fine. Let's see, it's asking for more. Let's AB, BC, CB, BC. So it's the same, but extended by BC, CB. Let's do that. So it's from A to B, B to C, C to B, and then B to C and C to B again. It's almost like it's getting into an endless loop. It is, isn't it? So it's got stuck. What we were hoping for is that it would find actually other interesting routes like A to D, D to E, E to B, but it's not going to get there because it's just going to keep repeating this part of the journey. It's found the basic one, A to B, and then it keeps adding B to C and C to B again, and it just keeps adding multiples of these, which is actually valid, but it's gone down a search path which isn't interesting. So it's not wrong, but it's not interesting. We would like it to say, okay, find A to B as one journey, and then find another one which is A to B, A to D, and then D to E, and then E to B, this one, and then maybe this one, rather than constantly doing this one, which is AB, BC, and then doing this endlessly, growing them. As you can see, that's happening here. And that's not interesting. So we're going to try and solve this problem. Before we solve that problem, let's look at another journey which is a little bit longer. So instead of from A to B, we are going from A to E. And that shouldn't be too challenging. You know, we can go from A to B and B to E, or A to D and D to E as probably the two shortest solutions. Let's write that down. J could be A to B and then B to E. Another one is A to D and then D to E. That's the second option. And then other ones would be kind of convoluted by perhaps going from AD, DE, EF, FC, CB for the journey from A to B. That's the long way round. Let's see how Prolog answers that. So instead of A to B, we're going A to E. Let's run that. And it doesn't seem to, well, there you go, it's run out of memory. So it went down some path that wasn't productive and exhausted its memory, the stack. So we know that that shouldn't be difficult at all, and yet Prolog went down some search journey which was not productive and just, you know, kept extending and extending and extending options and run out. So that's a problem we also have to solve. And before we do solve it, let's think a little bit about what we would do differently to what Prolog appears to be doing. Well, if I kind of gave you a piece of paper with this map and said find the journey from A to E, from here to here, your natural kind of approach would not be to find a circuitous journey from A to B to C to F to I to back to F to E. You wouldn't do that. Your natural inclination is to find the easiest, simplest, shortest journeys, and that's the clue. There's a heuristic there, a kind of a preference for shorter journeys. So shorter journeys in our construction of the problem means shorter search depths. So as Prolog tries to kind of find solutions for J, it's internally, as you know, it's building J and trying to see if it satisfies the journey property. And we can see in this case it's building and building and building J, and, you know, without success, and then it's run out of memory. So we need a way of either encouraging or enforcing a shortness of a journey, giving it a preference, or even just preventing long journeys. So that's what we need to think about. So we could do that by enforcing a kind of a limit of, I say, a length of the list. We could do that in Prolog. Yeah, we could do that. We could say in our definition of a journey, we could say the length of that list is, you know, less than 5 or something. Now, that's one way to do this, but it wouldn't illustrate the use of a meta-interpreter to alter and adapt a search strategy. So you can see how discussion has led to us to conclude that the vanilla search strategy is, in this problem, taking Prolog down an unproductive, endless, kind of infinite path that isn't giving us the quick, efficient sort solutions. So let's see if we can change Prolog's search strategy so that we enforce, say, a search depth. And that's given a name. That's actually quite a common tactic in computer science in general, in solving kind of problems. So fixed depth search is the name of the method or the idea, and even though it's fixed, it doesn't have to be fixed. You can try different search depths. So the idea is that you try maybe a depth of 1. So a journey might be from just one step, from say A to B. That clearly won't get you to E, but it's sufficient for A to B, but it's not sufficient for A to E. So A to E is what we're trying to do. So if a depth of 1 is insufficient, let's say we say there's a maximum depth of 2 for this journey. So A to B and then B to C is an option that Prolog could try. So AB and then BC, but it doesn't get us to the destination. We can backtrack and try AB and then B to E. Does that work? Yes, it does. So that does get us from A to E. So with a depth of 2, it finds that solution. And what we've prevented is Prolog going A to B and then B to say C and C to B and then B to C and C to B, which is what it was doing like this. It's getting trapped in that path. So if we had an enforced limit of 2, if it did try A to B, B to C as it did here, that's the end. It won't extend that further because we'll have enforced that. We just say nope, you're not doing any more. We could have a depth of 3 as a maximum. So 3 is the maximum depth. So we could try A to B, B to C, C to B. It's tempted to go down this path, but then it stopped. So that wouldn't be useful for it. So can you see the idea there that by limiting the depth of its search, which in our case means the length of that journey, we are preventing it from going down an endless unproductive search path, extending the journey A, B, B, C, C, B, B, C, B, C, B. We just cut that off and say stop, backtrack, fail that in the Prolog sense of fail, backtrack and try a different, go back to B, say, so A to B, A to B, and then instead of going B to C, try a different one because you've kind of done that now. So that's the idea of fixed depth search, and it encourages, as you can see, a more breadth oriented search rather than a depth oriented search, because as you know, Prolog by its nature, the way it solves queries is by working from left to right, as you remember. So if you've got a query which is defined like this, it'll do left to right, try and solve the goals from left to right, but it's depth first. So if to solve this one, it'll keep kind of trying to resolve that, and that could be endless. So you'll never kind of you'll never solve that full query. So we are changing the search strategy from a depth first approach to something that encourages exploring the breadth of solutions. So by breadth I mean not just going A, B, C, C, B, B, C, C, B, B, C. That's a depth first search. We're saying stop and explore the breadth of options. So after you've done A, B, C and not got anywhere, try A, B, E, and there might be others, but that's not the case in this example. So that's why it's encouraging more of a breadth search rather than just purely depth first. And we do that by pruning or snipping its attempts to go very deep. Right, so I hope that's can explain the idea, the heuristic. If you need to take that slowly, look at the blog, because the blog explains these ideas in better words, more carefully chosen words than what I'm just talking to you about, which is off the top of my head. So how do we do that in Prolog? How do we implement a fixed depth search? Well, let's have a think about that. So with our Prolog prover, we're building on what we've had before, And if you remember, the Meta-Interpeter has a line. To prove something, we have to find clause HB, and we have to find that query, and we have to find a property in the database that's relevant, get B, which is the body, and then prove the body. And we had a different kind of line to cope with the fact that B could be a sequence of goals. How do we change the core of this engine, as it were, to be fixed depth? Well, we obviously have to supply that parameter, so we change prove to be prove h a depth. So on first calling, we give it the maximum depth, and then we have clause HB as before, and then we prove the body, but now our depth has reduced by 1, so in some sense the D1 is D minus 1. Can you see? So this this call for prove will have the depth parameter 1 less than the initial one. So if we call prove something Q, so let's say 3, that'll end up calling prove B comma 2, and that might end up calling prove, I don't know, some other B. It's going to be 1. 1. So 3, 2, 1, and then prove maybe 0, and then we can say we call prove as long as that parameter is more than 0 or more than 1. So we stop once it's run out. So it's almost like keeping a set of beans, and every time we go through this cycle, this inductive step from head to body and proving the body, every time we do that inductive leap in Prolog, we take a bean away, and we keep doing that until we run out of beans. So let's look at the definition in code. I've just popped that there. I had deleted it while we were talking about the earlier part of the program, and you can see here the core of the Meta-Interpeter. It looks more complicated, but it's not. I'll explain why. So we've got prove h, and now we've got a depth parameter, and we're saying this is true as long as depth is more than 0. That's enforcing that we haven't run out of beans. So it's 1 bean, and we're saying next depth is that depth minus 1. So that's an arithmetic evaluation, and then we're calling next depth. We're calling prove with next depth. This has to be done before this. In my handwriting I did it after, but as you know, with Prolog arithmetic, you've got to have all the variables in the expression to be evaluated. You have to have them grounded, so that has to be done before this. So we call prove with next depth, which is 1 less than the one that was incoming. So that's the engine. That's just what we've talked about, but we have to adjust the arity of all the prove statements, because we now have an arity of 2. Instead of just prove h, we have prove h depth. So that one that copes with a body of multiple goals that we talked about previously just has depth added, and then we prove if there's a sequence, and that unifies with the head, then we prove A with depth, and we prove B with depth, and then that this is recursive. We are using in our program a built-in equals, so we have to have that handled. we're not using is, we're not using the cut deliberately, because otherwise we'd have to include that in our Meta-Interpeter. You can see why now we excluded the cut. And that was, as before, a equals b. But here we put an underscore because we're not interested in the depth here. We're only interested in the depth when we use prove. And the same here for true. We're not interested in what the depth is, but it has to be there as an underscore to maintain the arity. So let's see if that copes with simple examples. In fact, what I'm going to do is I'm going to add in to this Meta-Interpeter just the writing of the current rules that it finds successful. So I'm just so that we can keep track of what it's doing. So I'm going to write here, you can see what the depth is, and I'm going to write what the successful rules are as well. So this is including an explanation as well. So I didn't do that in the original code because it kind of extends the code and makes it look long and scary, but these are the only changes. I'm writing the depth and I'm writing what the relevant rules are which succeeded, and that's what we did last time. But the new thing here is depth, so we can print out and see the depth that Prolog has got to. Let's try prove on just a very simple query, which is not journey but connected. So prove connected a comma b, and we'll give it a maximum depth of 2. So remember, this is not the depth of j, not the length of j, the journey list. This is the maximum inductive steps that the Meta-Interpeter is allowed to take. So let's see if that works. Well, this is interesting, isn't it? This really shows the power of a Meta-Interpeter. You can see that it's saying we'll start out of a depth 2. A and B is connected because there's a link between A and B, but we're not finished with the proof yet. Now we say depth is 1 because we've taken one inductive step, and now link AB is just true because it's a database fact. So we are both printing out an explanation, and just for kind of debugging purposes, we're printing out the depths as well, just to see it working. Oh, okay, it tried backtracked, tried another one, and that was false because of this kind of backtracking there. Let's try if that works if we only allow one inductive step. That should fail because this one needed 2 to prove. Even though it feels like it's 1, it's actually 2 steps. Its first is that one, connected is true because the link is true, the link is true because it's a database fact. Let's try that. Yep, it couldn't prove that. So it found a relevant fact, connected AB, link AB, but as we know that's insufficient. We need to go further and say link AB is true as well. It's backtracked and tried others and not found anything. So you can see that even though this is, in the general world true, by limiting the depth of that the prover can take in terms of inductive steps, 1 is insufficient. If we did 3, obviously that would be sufficient. True. And that's more than's needed. So you can see there that by having too small a permitted depth, we rule out some solutions. In this case we didn't want to, but so there's a balancing act here where we start off with a shallow depth search to find any solutions, then we can iteratively increase the permitted depth to reveal more solutions without it ever getting into an endless loop, because it can't get into an endless loop because there's always a finite maximum. Let's now try our challenging journey, which was from A to E. So prove journey A to E with a list J, and we'll have a maximum iterative depth of 3. that may or may not be sufficient. Do you remember last time we tried this, it just got into an endless loop and failed completely, which is surprising because it's just from there to there, it's just from there to there and there to there, but it just got into it probably went like this. That didn't work, did it? So let's try and see if this works. Okay. I'm going to remove the writing of the depth because that's kind of too much on the screen. Let's try that again. Nope, it's not worked. In fact, I might remove all the writing steps. Back to our simple one. Yep, false. So that's saying it tried, obviously, as you can see it working out here. We could have written a trace, for example. This is almost like tracing, isn't it? So 3 inductive steps wasn't enough. Let's try 4. Yep, it found that. And which one is it? A, D, D, E. A, D, and D, E. I'm going to do that in a different colour because that's a celebration of a success there. A to D and then D to E, and it got that right this time. Whereas remember, without the Meta-Interpeter, it failed completely. It ran out of memory. It couldn't find that simple solution. So that's seeing the power of changing the search strategy with a Meta-Interpeter. So 3 didn't work, 4 did, and it found this simple one. You see that there's a preference for it finding short journeys. Let's try it. Let's see if it found any more solutions. No. And it didn't crash there because everything it tried had to have a maximum depth of 4. So it didn't crash. Let's try 5. That's the first one. No more. Does it need many more? Let's try 6. Ooh, on this one, its first solution is different. A, B, B, C, C, F, F, E. What does that look like? A, B, B, C. A, B, B, C, C, F, F, E. Is that what it did? Yes. So it found this way around. Anyway, we can keep playing with this. But the main point here is that we have a new strategy where we start off with a very low search depth. We increase it slowly. We can even jump, say, straight to 4. Find a solution which was impossible using the vanilla Prolog approach, and has been made possible by using the Meta-Interpeter to enforce a maximum depth to the Prolog search so that it exhausts what could be endless kind of search loops, and terminates them at that maximum depth and then moves on to a different path to explore. So that then reveals solutions which wouldn't have been otherwise. Fantastic. So that illustrates the idea. I hope that's been really interesting and useful. For me, I think this really is a fun example. It's about solving mazes or finding journeys, journey planning. But the main idea was to illustrate a different use for Meta-Interpreters. Up to now we've been focusing on learning about Meta-Interpreters, so we kept it simple and all we did was print out explanations. Here we have a very different scenario, a different use for Meta-Interpreters, which is to actually change the search strategy, and you can see there's a use for it. I hope that has been exciting for you. Certainly is for me. I'm still kind of excited by the magic, as it were, of Prolog being able to not just find and solve logic kind of problems, but actually the ease with which it even allows the strategy that it uses to be kind of changed. And you can see how that hasn't been particularly difficult. All the code that we've got here fits in a page. If you think about other languages, Python, C, Java. Doing something like this would not have been as easy at all. Even writing a meta-interpreter in those languages is not easy. So that concludes the journey for now, and it concludes the planned 20 examples, and you can see them on the blog. If you go to the top, there's the contents, and you can see there's 20, and we've grouped them by theme, so very simple basics, and we did recursion. That was a really important concept. We looked at the cut, and then we kind of leapt forward with what seems like a very kind of advanced topic, but as you've seen, it's not that difficult really. And that was meta-interpreting. What I'll just briefly do is talk a little bit about terminology. So I have deliberately chosen up to this point to avoid some of the terms or the terminology jargon that a lot of the textbooks and courses use, and is actually part of the world of Prolog, because I found them to be unfriendly and not very helpful when you're completely new to Prolog, or if you are already struggling with it. So it's worth just kind of covering them briefly for completeness, especially if you're going to go on and use those other more comprehensive tutorials and courses. So we've talked about property. The proper term is predicate. So when we've talked about things like fruit one, those are predicates, like ancestor, and even the built-in things like equals and is, they are predicates, and predicates can be true or false. And you can see why we use the word property, true or false. But predicate is the jargon, as it were. Feel free to kind of look up the proper definition when you're ready to, but there's absolutely nothing wrong with using the word property for our journey up to this point to help get the ideas into our minds. You'll see the words term and atom used. So an atom is like a constant. We called it a thing. That did sound a bit odd. We referred to things, and I emphasise them in the kind of discussion. But the proper term is atoms. So apple, orange, Sally, a banana, cat, dog. Those are atoms. They are constants. They're not variables. Remember, variables have capital letters, and we did use the word variable, and I think most people can understand that. All the data objects, whether it's atoms, numbers, variables, all of those things are called terms. You might see a functor, the word functor. It's like computer science jargon, but it's the name of a predicate. So you might say, why would you use the word functor instead of predicate? So functor is relevant when you're talking about the syntax, like the arity and whether it's infix or that sort of thing. And sometimes with more advanced Prolog you can set priority, like you can have arithmetic priority, like times takes precedence over plus if you don't have brackets, that sort of idea. So functor is when you're discussing the syntax, and predicate is used when you're talking about the logic, and that's because the origin and the source of those words come from different sets of discussions. So functor is about talking about syntax, and the word predicate comes from the world of logic, which is talking about true and false. And it's not function, just to be clear there. So that, just for completeness, I wanted to cover some terminology. It's all on the blog. You can have a look at that. There's obviously this YouTube channel. All the code is on GitHub, and you can kind of copy and paste it or have a look at it there. It's all there. And if you'd like to support this work, feel free to recommend the book to your friends. That kind of helps pay for this effort. Going forward, what we'll do is pick interesting small examples beyond these, and turn them into tutorials on the blog and on the YouTube channel. So one of the ones I'm thinking about might be to use Prolog to output those search trees that we've drawn by hand before, That's quite a challenging thing to do, but that might be an interesting future video. Or if there's any specific question that pops up from your feedback, your kind of comments on the YouTube videos, for example, that might turn into a topic for a video. So do remain engaged, and do pop in questions, and we'll see if we can answer them or turn them into a video. Fantastic. So that's goodbye from me for now. I hope that's been useful. I hope I've achieved my core objective, which is to get you, if you were struggling a little bit, just over that initial hump, that gap from not being feeling confident with Prolog at all, to the point where you can understand these ideas, these core concepts, and then they're ready to take on the fuller courses, whether it's your university course or whether you're self-teaching. Fantastic. Take care. Bye.